Welcome to the secret life of MLCCs, beyond the datasheet. In this video, we'll take a deep dive into the real-world behavior of ceramic capacitors. We begin with a common engineering problem, a circuit acting wonky and making hissing noises. The root cause was often the humble ceramic capacitor. The behavior of an MLCC is defined by its dielectric material, categorized into two main classes by the EIA. Class 1 offers predictable, linear performance, best for precision circuits. Even before advanced effects, a capacitor's value varies. Tolerance and the temperature coefficient of capacitance, or TCC, guarantee it will vary from the nominal value specified at 25 degrees Celsius. For Class 2 capacitors, applied DC bias voltage is the single most important factor beyond the datasheet. The effective capacitance decreases dramatically as DC bias voltage increases. This DC bias effect originates from the crystal structure of Class 2 ferroelectric dielectrics. With no bias, high capacitance results from randomly oriented polarization domains. Applied bias forces the domains to align, lowering the dielectric constant and capacitance. The DC bias effect is not merely theoretical, it's a direct cause of circuit instability. It impacts high-risk applications like buck/boost regulators and filtering, where circuit performance depends on minimum capacitance. Ferroelectric materials in Class 2 MLCCs are not perfectly stable. Over time, internal stresses relax, causing the capacitance to decrease, a slow drift known as aging. DC bias accelerates this aging effect. This phenomenon, known as DC bias aging, is a field failure mechanism that results in a time-dependent capacitance drift larger than standard unbiased aging. Beyond capacitance, Class 2 MLCCs introduce other complexities. Electromechanical resonance can cause the capacitor to vibrate and produce audible noise. Also, derating has limitations and doesn't prevent all failures. Taming this complexity requires a three-part approach. First, design for effective capacitance under worst-case conditions. Second, select intelligently, favoring stable Class 1 or mitigating DC bias for Class 2. Third, simulate, don't assume. Your most powerful tool is manufacturer simulators. These web-based tools allow you to plot effective capacitance against DC bias, temperature, and AC voltage, providing real-world values for your calculations. The nominal capacitance is only the tip of the iceberg. To design robust electronics, we must look past the tip and account for the vast complexities hidden beneath the surface, including DC bias, TCC, and aging effects.